So we'll do a quick flyover of safety devices and circuits, kind of give a quick review of that content in preparation for the exam too. So in this unit, we talked about grounding, and that's equipment grounding versus system grounding. And so if we're looking at two different types of grounding mechanisms or techniques, and then we have minimum grounding sizes for our ground conductors. We also discussed GFCIs and how we connect those. And then overcurrent, specifically circuit breakers, fuses, and motor heaters. And then some HAZ location. And this we didn't get to in lecture, but I'll hit some of that in this video. And again, our goals for this unit were properly wire electrical circuits per safety considerations, especially grounding, and then select safety devices appropriate to code and regulations, and that's the GFCIs, the motor heaters or overloads, and the circuit breakers and fuses. Understand the difference between human and equipment safety, and this really comes into play when we talk about grounding and GFCIs and circuit breakers and fuses. And then arc flash, explosion proof, intrinsically safe, that's our hazardous location equipment. So we're calling equipment grounding. Really, that's when we have the piece of equipment, whether that's our drill or our box or our CNC machine that we have here, and we have a ground conductor connected all the way back to the grounding bar in the power distribution panel. And so that's a connection specifically from the chassis or the housing of the piece of equipment back to ground. And eventually that literally will go into the ground, into a ground bar. System grounding then is where we take the actual connection from the panel into the ground, okay? And so here is equipment. And then this point here is our system. And we can show that on this page here, where we actually take a ground bar, actually two ground bars, and we connect them to our ground bus terminal point in our electrical enclosures. And the two sides of this panel have two ground buses. They are going to be internally connected so that they're both grounded. And once we add this connection here, we've now made that system grounding point, okay, because we've grounded the main power distribution panel, that main grounding point in the system, to ground. A little difference between equipment grounding versus system grounding. If we look at the minimum grounding conductor sizes, if we have copper, so we have a copper column and then we have an aluminum column. If we notice here, the gauge for our aluminum is always going to be slightly larger because the conductance of aluminum is not quite as good as copper. And so based on the rating of our circuit breaker that we have, 100 amp circuit breaker, we would use an 8 gauge copper or a 6 gauge aluminum. Similar with, so this is our system grounding. So this would be system grounding. Oh, this would be equipment grounding. Okay, so this is our equipment grounding conductor sizes. And then if we have our system grounding, and we have a size of the largest service entrance cable conductor, so the lines, the hot wires, if we look at those, and we have a 2-aught or 3-aught, then we're going to have a copper 4 conductor. If we have an aluminum 4-aught, then we're going to have aluminum grounding of 2-aught or 2 gauge. So you go based off of the line size, whether copper or aluminum, and then here is the grounding. And usually GND ground is the conductor that we would use. If we looked at GFCI wiring, if we notice that we have our line, our hot, or our line from our panel feeding into the line, as well as the neutral from the panel feeding into our line. It's very important when you have a GFCI that you have the input is the line, and then anything past the GFCI that you want to protect with that GFCI, you come out of the load. And I can have up to 3 of these receptacles after a GFCI to be protected. More than 3, I have to get a second GFCI. We then looked at circuit breaker trip curves, and really what we're looking at here is along our x-axis we have the multiples of current, so 1 times, 2 times, 3 times, and then we have our time, how long it takes for that circuit breaker to trip based on how much current multiple is flowing through the current, flowing through the circuit breaker. So if I have a 10 amp circuit breaker and I have 4 times that, so 40 amps, that's going to take almost 1.5 seconds, right, to trip. That's the concept of how we interpret those graphs. Specifically looking at more of a trip curve that you would see for an actual circuit breaker. This on the left is very generic. On the right is more traditional, what you would see if you pull up the trip curves for that circuit breaker. You're going to have a couple different regions. You're going to have a magnetic trip region. So anything in this part of the curve is almost instantaneous. It's going to trip very quickly. The thermal trip section, right? That's anything kind of on this more gradual slope. That's where ideally you want to design or select that circuit breaker for to trip at. And anything in this middle point is the in-between. And of course we have a top and bottom, or low tolerance, high tolerance, the quickest it will trip or the longest it will trip. And so as you go up in a vertical direction, you're going to hit the bottom curve, part of the curve, right? My hand's right here. First, that's the quickest it will trip, and then the high point is the longest it will trip. So there's a dead band, there's a tolerance like we have in most things in life. We have the fastest it's going to trip versus the slowest it's going to trip, and it's always a range. This is a typical trip curve with multiple types. So we had a B here. I can move this out of the way. We had a B, which will trip fairly quickly. A C will take a little bit longer to trip, and a D even longer to trip, given the same amount, say 5 times or 3 times or 10 times, right, the current. And so we can decide what type of circuit breaker we use based on how long we want to hold the circuit breaker from tripping. And so a lot of times that is a question of inrush current. I have current here, time here, and I know that my motor is going to have this huge inrush current within this steady state current. I want to get past this high point, and that's a certain amount of time, okay? And so the farther I go this way, the more time I have to withstand that inrush. And that's really a big takeaway. And so we're trying to pick that point, pick that circuit breaker type based on how long of our inrush, based on how much multiple of the normal current. So if I have a 100 amp circuit breaker, but it's 5 times, so it's 500%, 500 amps, how long will that take to trip a class D circuit breaker? It will take anywhere from here to here on my class D circuit breaker. So here's my class D. And it will be anywhere from here to here. So that's 1.5 seconds, all the way to, it looks like 7.5 seconds. So of course there's a dead band, there's a range there. Switching over to the advantages, disadvantages of circuit breakers over fuses can be used as a switch. So a circuit breaker, you can use it to turn off the circuit. You can actually lock those out, lock out, tag out. Less prone to tampering, easy to re-energize. You just flip the switch back on, the circuit breaker back on. It's a little bit harder to replace. You got to pull it out on wire, put it back in, rewire. Whereas a fuse, you can just unscrew and screw back in. Looking at fuses, similar process to interpreting their trip curves, except we have different curves per the different currents that we have. So if we had a 10 amp fuse and we have 30 amps of current going through that fuse, it will trip in about 0.2 seconds is what we determined. So again, you're following up vertically till you hit the curve and then going over horizontally until you find that time. You could do it the other way. You could go from Y to X. So if you have a certain number of time, how much current can you withstand for that amount of time? You could do it that way as well. Advantages, disadvantages for fuses versus circuit breakers. A fuse usually has a lower installation cost. Fuses are oftentimes higher reliability. So a lot of times sensitive electronics have fusing, not circuit breaker for protection locally. There's a higher current capability for fuses, and a lot of times it's a little bit easier to lock out the fuse. You just pull it out and then it's not there. If it's in your pocket, it's harder to put back in, or if it's in a locked box with your lock and tag, then it's harder to put back in. You can't cut the locking mechanism off of a fuse if the fuse is not even there. Then we looked at motor overloads or heaters, and has a similar process to interpreting their trip curves. The one difference we have here is we have classes, and so class 10 will trip faster than class 30s, and we have a cold trip versus a hot trip. So if it's hot out, that's going to trip that overload much quicker. And if it's cold out, a lot of this tripping is based on thermal temperature of the element inside that overload. And really the overloads we are using to protect our motor. Nothing else, just the motor. Circuit breakers, fuses protect the conductors, the wires. Motor overloads or heaters protect the motor. And then hazardous location equipment. And so there's a couple things here to be considering. There's some videos that you could watch, pretty interesting grain dust explosion videos. But really we want to think about two different types or divisions and classes of explosive environments. And so we have the class, which is class 1, 2, 3. That's where we're defining the flammable or combustible, ignitable things in the air that actually make that fire explosion possible. And then we have the divisions, which is the flammable substrate are continually present. So the divisions is how often those materials occur, right? And so usually the higher the class, the more stringent that environment is, the more careful we have to design our electrical equipment. And the way to do that, we can have an explosion-proof equipment where it contains the explosion. If there's a spark inside a piece of equipment, it will contain that explosion. We can watch this YouTube video to see one of those explosions being contained inside of a really, really heavy-duty enclosure. This is for high voltage, usually above 50 volt circuits. And then we have intrinsically safe, which is our low voltage. You can literally have two bare wires, theoretically, sparking in open air in that explosive environment, and an intrinsically safe barrier will keep that incident energy at a low enough level that you will not get a spark to explode the environment. And so that's where we usually see those in low voltage scenarios where we're just looking at the sensors in that environment. And then of course, arc flash, PPE, as you turn on or connect any type of switch, there's going to be an arc as the closer that those two contact points get to each other. This actually happens every time you plug in a cord into an outlet. There's a little spark. Of course, it's inside, so you can't see it, but the bigger piece of the equipment, the bigger that spark's going to be. And so we have safety PPE to protect humans as they are close to those environments. And really what this graph is showing is we have our enclosure here where I have my switch and it has that arcing happening, and there's different zones that you can and can't be in, and really qualified individuals are the only ones inside this large zone area. But then as you get closer and closer, the level of PPE increases. And so if we look at that, that's defined by the flash boundary, right? There's a distance, and also the incident energy. How much energy capability does that piece of equipment have if it arcs? And so then we have these approach, limited approach, restricted approach, and prohibited approach, which correlate to all of these zones here. And the PPE that we can actually envision are from least to most, and depending on the severity or the level of incident energy. So that's the safety devices unit, quick overview. You can also look back at the lecture slides as posted. So good luck in your studying.